This is a secure programming presentation, but it's not intended to be complete. In fact, there's no possible way I could expound a complete secure programming, defensive programming, secure software engineering doctrine in 30 minutes. Instead, I want to just do a series of case studies of security issues I personally have encountered in programs I worked on. And the main takeaway I want you to get from my presentation today is not the specific outcomes of the case studies that I'm showing you, but more to encourage you, if you are a developer or if you're working with developers, to go beyond what is the security bug, what is the fix, and actually look at the contributing factors and the underlying causes and work out a doctrine to address those. So let's start with the Tag Pki, which is a lovely 20-year-old enterprise Java beast, which is just so much fun. And it's one of the main projects I work on. Like all big enterprise systems, it has an access control regime using access control lists. This is an ACL for dog-tag. The anatomy shouldn't really be surprising to anyone who's ever seen an ACL before. So basically, there's just a resource, a series of operations that can be performed against that resource that this ACL governs, and then, in this case, 3, but a number of access control rules that basically say, we're going to allow or deny these operations against this resource to accounts or tokens that satisfy these predicates. So in this case, anybody can list or read the authorities in the instance. Administrators can create, modify and delete, but Mallory, whether she's an administrator or not, may or may not be able to create, modify, delete the authorities, depending on this configuration, the evaluation order. So if you've seen Apache access control configuration, you will have seen something exactly like this. Basically, it's just a global configuration that says, do we process the deny rules first or the allow rules first? Okay, so that's the setting. Here's some code for processing the access control list. It's simplified, but this is the basic idea. If the order is deny allow, we're going to grab the deny entries, we're going to run over those entries, and if any of those entries match the user's authentication token, we're going to throw an exception saying permission denied. If the order was not deny allow, so if it's allow deny, then we do that for the allow entries. And by now, some of you have probably seen the bug already. The second step is to do the same thing, but for the second part. So if it's deny allow, then we get the allow entries and process them. And if it's allow deny, then we get the deny entries and process them. And in the second stage, instead of kicking you out, if the rule matches, we let you in. Okay, so who saw the bug?
Getting the allow method function when you should be looking for deny.
Yeah, exactly. So if the order is not deny allow, which is the default, if it's allow deny, you're going to grab the allow entries at this stage, but then if any of the allow entries match, we're going to kick you out or reject the operation. And similarly, in the second stage, if the order is allow deny, we're going to grab the deny entries, but then let you in if the deny entry matches. Yeah, so is everyone following? Yep, sweet. So does anyone know what is the phenomenon that leads to a bug like this? If you know it, just shout it out. I'll say it's Boolean blindness is what it's called. Anyone heard of that? So a Boolean value is just true or false. What does that mean? What does true mean? What does false mean? In this case, on this particular slide, in the if expression toward the bottom, you're running this evaluate subroutine and it returns a Boolean. What does that Boolean mean? What does true or false mean? In fact, it means that the rule matched the token, and that's all it means. But it was interpreted as the permission is denied. And exactly the same thing happened on the next slide, but it was misinterpreted as the operation is allowed. So this is Boolean blindness. It's a pretty common sort of bug. It can lead to security issues and many other kinds of failures in programs. So when you understand the underlying issue to be Boolean blindness, then you've got to go beyond fixing the actual bug and ask, how can we prevent these sorts of bugs from arising in the first place? Oh, there was a CVE assigned for this. Actually, we think the impact was very low. We think it's potentially catastrophic, but we think it's very unlikely anyone was actually impacted by it because all the rules have their sense reversed. The behaviour is going to be so busted, and if the allow rules are kicking you out, basically no one's going to be able to do anything. So we think it's very unlikely that anyone would have changed this configuration and not noticed that everything was busted and reverted it. So we don't know, and we don't think that anybody was actually affected by this, but nevertheless we couldn't be sure, so they filed a CVE for it. So the principle here is basically avoid Booleans. Use Booleans as little as possible, and instead use custom types to express different cases of the operation of your program. The corollary is that you need to use tools, programming languages that support lightweight, easy creation of custom types. So you can use enumeration types in these languages, Java, C#, and so on. Python has enums. They're strictly typed, so they don't compare equal with, with integers or Booleans. But of course, it's dynamically typed, so it's going to end up being a runtime error rather than excluding a program at compile time. And on the bottom line, programming languages like Rust, Haskell, and so on let you go a lot further along these lines with full algebraic data types. So to fix this issue, basically we just introduce a bunch of enums to express different variables. So the ACL order is now an enum type, the ACL result is allowed or denied, and then we refactor the code. I'm not showing it all here, but we refactor the code, and instead of using Booleans to express the results of particular computations, we're going to use these enum types. So we no longer have the potential of Boolean blindness where a developer gets confused about what true means or what false means. The value actually says what it means. Okay, so that was case study one. The second one, FreeIPA, the other main program I work on, an identity management system. So it does LDAP, Kerberos, host-based access control, certificate authority, which happens to use dogtag under the hood. When you're performing operations against the CA, the block diagram looks something like this. The user talks to FreeIPA with a Kerberos ticket to authenticate the user. FreeIPA, when it talks to the LDAP database, acquires a proxy ticket to operate with the same credentials as the user, so operating directly on behalf of the user. But when FreeIPA talks